everyone. Before I start, I would like praise the organization, this workshop by Julian and Jacqueline, she's there, and Juarez, and Paula. Paula, it's very nice job you have done here. My talk is about GROMACS program, and I divide this presentation in 4 different topics. I have a few words about history of GROMACS, some words about GROMACS capabilities, operation, and tools. We have a look about the GROMACS input files and protocol. And by the end, I will show you and just show it the main systems you can treat using GROMACS, okay? Let's go. GROMACS stands for Groningen Machine for Chemical Simulations. It's a software developed main focusing on biomolecular systems like proteins, lipids, nucleic acids, etc. And most of the information I will talk here you can found at the GROMACS official website, okay? Although the GROMACS is mainly focused in biochemical systems, biomolecular systems, it has been used a lot in material science too. It makes it very interesting for our division because there are wide variety of materials you can use it. Among other things, GROMACS can do molecular dynamics, conventional molecular dynamics, shell molecular dynamics with polarizable models, simulated annealing, stochastic dynamics, Brownian dynamics, energy minimization, and so forth. Advanced techniques for sampling is also implemented, like constraint algorithms, essential dynamics, expand and ensemble, replica exchange. Free energy and PMF calculations, it's also implemented, which are very important techniques to study process and systems as well. So you see, it's a very comprehensive software when it comes techniques, integrators, okay? GROMACS was firstly developed in the biophysical chemistry department of the University of Groningen, Netherlands. This is between 1991 and 2000. Its main routines, it was rewritten from the GROMACS software, an old software based in Fortran 77. The 2 groups has developed. The GROMACS started at the same group, and from then on, this group is split up, and the software became developed independently. By the way, GROMACS is still a very important software using exclusively to biomolecular systems. Since 2001, GROMACS has been developed by these teams in Royal Institute of Technology and Uppsala University in Sweden. And the head authors of the GROMACS is these 3 guys, Eric Lindahl, David van der Spoel, and Burke Hess. This is another important name, Mark Abraham. Mark is a development manager of the GROMACS. He's it's fun, he's a source of fun by himself. His peculiar mood and a little bit intolerant of newbies, but a very clever guy. Yeah, it's nice read these replies from the community. In 2008, David van der Poel has visited UFSCar for a meeting organized by Gomide and André Farias. In that occasion, someone asked him to more analysis tools, and he replied to them something like that don't ask what GROMACS can do for you, but what you can do for GROMACS. So this reflects, it's a little bit of the philosophy of GROMACS developing process, okay? So GROMACS is a free software, is an open software. All can contribute, all contribute as welcome, are welcome. And they have been a great use of this philosophy because they, today we, there's a larger group of developers, core developers around the world, and another contributors too. Okay, this guys is so important, not only by the developing of the code, but to the dissemination too, giving seminars, web seminars, hands-on, and mainly to answer questions to address to the community. This is most important. Nobody knows the GROMACS like these guys knows. So it's so important to community. Since I start use GROMACS in 2005, around here, GROMACS it's changed dramatically, okay, and you can see that because GROMACS became even more flexible, more faster, and with far more capabilities since 2025 in this last 15 years. Well, by the way, capabilities is a new topic in this presentation. Speed. Speed is a kind of obsession of this team. If there's room to gain a delta second in each routine, they do it. This places GROMACS as the most faster MD software in the world. They're running 3 up to 10 times faster than the similar ones. This is an easy install software too. You just download it in your official website and compile it by yourself. If you're a Linux user, you just use apt-get to install GROMACS, or if you Mac user, you can simply use brew, install GROMACS, okay? It's automatically. Because GROMACS is open software, you can change it and improve it, and so contribute back to the community if you wish. By the way, this GROMACS community is very activity. You can find answer for virtually any problem you can came across, okay? Just searching in the user list. But of course, for novices, I should recommend that you need to make a careful research about your problem you are facing before posting that list, so you can receive a reply of the kind Mark Habram, something like that. Very basic question. They should go back and read the manual, okay? Or more inspired that, something like that. I need to blur this guy is not Brazilian, but by the way, by chance, somebody knows. When you get some advice, it's good politics to be follow those up or reject with reasons before casting about widely with their other theories. You don't want to people giving free advices, feeling like you are wasting their time. So this is not a characteristic on Mark Habram. Most of developers and molecular modeling has this kind of treatment with the people, because see, it is a very like Axel Kohlmeier from do you read? But Alex Kohlmeier is not so patient too. Okay, beyond that, the capabilities I have mentioned before, GROMACS provides extremely high performance. Okay, since GROMACS 4.6, it has excellent acceleration on GPUs. GROMACS also is user-friendly. Files like topology and parameters are written in a clear text format. There are a lot of checking, consistent checking. This is making it almost foolproof. And it's difficult to do anything wrong here. All GROMACS programs use a simple interface with command lines options for input and output file. For every single program on GROMACS, you have a short manual you can access using -H option. Okay, it's so easy to learning. For novices, this is a very, very interesting option. GROMACS can come with a large selection of flexible tools. I told you a little bit later about it, but so you won't have to write virtually any code to perform a routine analysis in GROMACS. Okay, it's everything. It's built in. GROMACS has interfaces with both quantum chemistry and bioinformatic methods. And the most interesting, all of this is for free. Okay. Okay.
What group are the main developer of GROMACS today?
Yeah, I told that. There's a core of 4 guys in Sweden treating with them, but there's a spread around the world, and you have many collaborators around the world. Here in Brazil, I believe Tuanan spent time there, not Tuanan. Luciano, the advisor of Tuanan, spent a time with David Van der Spoor. You too, no? GROMACS has a large number of analysis tools. And it's around 90 different tools. It's a large number. Think, to get an idea how large it is, think about the program you have been used lately and compare it. Okay? I bet it should be less than GROMACS have. So all these tools are classified by topics. If you wanted to make molecular dynamics simulation on material science, this bold one should be most interesting to you. Trajectory analysis, processing energies, mass, structural, kinetic, and electrostatic properties. Interfaces properties is also important too. Okay. Let me talk a little bit about the typical GROMACS protocol. As lumps, as Julian said, GROMACS also needed 3 different files to start a simulation. You need a configuration, start configuration. All mechanical problems need that. You need a system topology, which has any physical chemical information about the system to be studied. And the simulation parameters. In this file, you need to put all information about the system and conditions of the simulation, okay? Having these 3 files, we can follow this flow. First, you provide to GROMACS a PDB file, the starting configuration. Everybody knows how a PDB file looks like. It's something like that, okay? You have name for atoms and molecules. You have the atomic position coordinates, X, Y, and Z. This is just a set of geometrical points with any physical chemical meaning so far, okay? This file is just a single water molecule. If you have a box with 1,000 molecules, you have a 3,000 lines here in this file, okay? Well, when this tool receive this, get this file, it will convert this file to GROW, a conf GROW. This GROW is just similar, but simpler than PDB, and you generate the topol.top. Top file is by far the most important file in your job because he's received all physical chemical meaning of the situation. And a topology file it looks like that. For water molecules, you have the name of the molecules. You have Lennard-Jones parameters, bonded and non-bonded parameters. You have charge. You have the distance between atoms. You have the angle and between the bonds. You have the constants, force constants, dihedrals, improper dihedrals, and so forth. Depends on the complexity of your system. So you have these 2 files. The GROW file you can edit as you wish. You can change the geometry. You can increase or decrease the volume. And then you can put inside it a kind of solvent you need. For example, you have a protein in the center of your box. You can surround it by water, liquid, for instance. And then with these the 2 files, you can pre-processing to check the consistency of the information it passed to the program. But before that, you need to provide also parameters of the simulation. This MDP file is something like that. In that file, you can inform the integrator. It can be molecular dynamics, stochastic dynamics, or energy minimization, whichever. And the time step, 2 femtoseconds here. The number of steps, the control during of the simulation. And you can make some options about the output control. For instance, in this case, position and velocity will be saved each 500 steps, while the force is never saved, okay? So the volume of the data you can control here. There's another kind of information like electrostatic treatments with cutoffs and treatments, modifiers of the potential, something like that. You can have informed properties about the barostat and thermostat, like temperature, pressure, bonds, constraints, okay? This is a bad choice, according to Kalini, because I constrain all bonds in my system. It's not good, good idea, but this is just example, of course. Then you have these three files. These two, GROM-PP preprocessor, will check in the consistency of this file. If it's okay, will generate to you a TPR file. A TPR file is a binary file which have all information you need to the simulation. From then on, you need only this file. This is another. This is not important anymore. And the simulation is straightforward from that. You can use just GROMACS run on this file tuple, and you got your trajectory and your energy file, okay? In GROMACS, we have three different types of force fields, namely all atoms, force fields, united atoms, and coarse-grained. In the first one, you have parameters for every single atoms in your systems, like that. In this, we have parameters for all atoms, but no polar hydrogen, like that in alkyl chain. Okay, you have polar atoms aqui, it's omitted, should not be, but here we will not have. This is not anymore a carbon atom, but is a united atom on single side, two methyl or ethyl groups. And you have coarse-grained. This approach is an abstract representation. You can put together a bunch of atoms, and they represent a single site in your simulation. In this case, you can speed up your simulations by 2, 3 orders in efficiency. So from here to here, you have increased your efficiency, but from here to here, you decrease your information you can extract about your system, like in some specific interactions or things like that, okay? Specifically, there's very accepted force fields implemented in GROMACS, like Amber, Charm, Gromos, OPLS, Martin, the coarse-grained zone. And this is, as I said, is a very acceptable force fields. And with them, you can simulate a wide variety of material systems, mainly for these organic ones, okay? Most of, like those I show you to you now, okay? There are some limitations, okay? LAMPS and MD share these limitations because it's intrinsic of MD technique, but GROMACS has an additional downside because it's default release don't deal with reactive force fields. Neither those specific force fields for inorganic matter. So in general, I can say that for thermodynamical properties, GROMACS is unbeatable, but for mechanical properties, the LAMPS should do the work. When GROMACS is advantageous, GROMACS is much faster and simpler than most of other programs. So frequently, it will be the best choice, particularly when your system is organic, or you need to advance in sampling to describe your process, like PMF or free energy calculations. Which systems we can treat using GROMACS, okay? I show you a couple of works published in my groups in recent years. I could do it for outside groups, but I feel more comfortable talking about my work instead the others. There's many works using GROMACS in material science, of course. I invite you to search in that. Some years ago, I've been interested in peptide nanostructures. This structure is so interesting because it's biocompatible properties. You have a single polypeptide can self-organize in membranes, in nanotubes and nanorods, okay? And this makes so very beautiful jobs in using GROMACS here. This is a biodegradable materials. It's just amino acids, okay? Since before CINE, you had interested in carbon nanostructures like nanotubes, fullerenes, graphenes. This kind of systems is really easy to treat using GROMACS. And now, in the scope of this project, we studied supercapacitors and batteries that required information about electrolytes. Electrolytes, like ionic liquids, or aqueous ionic solutions is commonplace to GROMACS treat. It's a very simple system to GROMACS, okay?
How do you set up the initial position for all those molecules, those configurations?
Nice question, Juarez. This can be generated with homemade scripts, or the most clever solution is using a code PACMOL from Martinez or UniCamp. This PACMOL is a nice software you'll be addressing in our tutorial hands-on later today or tomorrow. Okay, here in this slide, I have example of the other part of the supercapacitor, the electrodes. We have here two electrodes based in amino acid, and here a graphene oxide based electrode. This is another job done exclusively using GROMACS. And of course, VMD, PACMOL, and all of the stuffs around the job. Last month, we had this paper accepted in PCCP. We have a graphene electrode coated by 660 molecules, and we were be able to show that capacitance of the systems coated by fullerenes increase for all electrolyte investigates, include the aqueous one. This is a remarkable result because you can assess the few informations from experimental results available so far. And we were glad to know that this paper has been a general choice for the collection of hot papers in PCCP in 2019. Okay, this is a fantastic, wow, nice job. No, not so much. It's just not a big deal. It's just a recognition of the quality of the work we have produced here in CINE. Okay. Okay, I'm finishing. I just share with you a short description of our hands-on starting later today. Tuanan is the guy for the first class. He introduced some concepts about GROMACS, describe the main files, and you simulate some simple systems like diluted solution and calculate these structures. Tomorrow I'm gonna talk about more advanced issues like that Juarez asked me about the generation of boxes and some VMD features to plot visualization. I have important too because it's so connected with GROMACS by itself. And I will simulate a little bit sophisticated systems like nanoparticles or infinite systems. And the last day, Gustavo's gonna talk about the advanced techniques like PMF, free energy calculations. He used homemade scripts, okay, to generation free energy directories calculations. And by the end, if I understand well, Gustavo, you're gonna do this like a membrane PMF across the membrane, okay? Okay. So, yeah, it's all for now. Thank you for your attention.